We are next going to look at accelerating systems. Whenever we have an accelerating system, that means that the forces are unbalanced. This means, for example, if you sum your forces in the x direction, you get a number other than 0. And remember, force equals mass times acceleration, so looking at the idea that force net is equal to mass times acceleration net, that means that if you have unbalanced force in the positive x direction, so you sum them up and you get a value that's positive in the x direction, you end up with an acceleration in the x direction. So rather than having constant velocity or being at rest, now your system is in motion and is in motion with an increasing velocity in the x direction. You could also have a situation where you sum your forces in the y direction and you end up with excess force, so you sum them up and you end up with like negative 10 newtons. So that means that the object has excess force in the negative y direction, so the system is going to accelerate in the negative y direction. So your force direction is going to match your acceleration direction, and if you have excess force, so when you sum all the forces, they're not balanced, that's going to lead to an acceleration and a change in velocity. Now, we think about the x and y system independent here. You could have net acceleration in both the x and the y, or you could have the system be at rest technically in the y direction, but be in motion in the x direction, or vice versa. So for a lot of problems, you might be moving along a horizontal surface, so the y is still balanced, and it's x where you have the excess force, and therefore the acceleration in the x direction. Alright, so now let's look at this example problem. We have a large Christmas present. Alright, so we're going to use a box to represent a Christmas present. And it has a mass, so we're going to take note of its mass. And it's being fought over by two children on a horizontal frictionless surface. So we're sitting on a horizontal frictionless surface. Child A pulls on a ribbon with a force of 200 newtons at an angle of 25 degrees below the negative x-axis. So we're going to be pulling down this way, 25 degrees, so this is force A. And then child B is on the opposite side, and that child is pulling up this way with 300 newtons at 35 degrees. And we want to know what the acceleration in the present is in the x direction and what the force normal from the surface on the box is. Alright, so since everybody seems to be tugging on this Christmas present, the object we're going to sum forces on is the present. Alright, so let's identify all of our forces. Alright, so what is touching the box? We have child A and child B. So we're going to have force A from the child, and that's going to be negative x, negative y, because the child is pulling down and backwards on it, because we're below the negative x-axis, and that puts us in the third quadrant. We're going to have force B from child B, which is going to be positive x, positive y, because the child is pulling up and forward, so first quadrant. And the other item touching the box, or present, is the horizontal frictionless surface. So since the surface is horizontal, normal to that would be the positive y direction. So we're going to have a force normal in the positive y direction. And then the box has mass, so that means there's going to be a force of gravity acting in the negative y direction. Alright, so now I need to draw my free body diagram. So I'm going to have force normal straight up in the positive y, force due to gravity straight down in the negative y. Force A is going to be down here in the third quadrant. So let's see, this was 25 degrees in here. This is force A, and then force B is going to be 35 degrees in here. Alright, so those true forces we need to split in the components, force A and force B. So we have force A in the x, then force A in the y, and then force B in the x, and then force B in the y. Alright, so now we need to write our x and y equations. So in the x direction, we have force A in the x, and that's going to be negative. And then we have force B in the x, and that's going to equal mass times acceleration in the x. We're looking for the acceleration in the x direction, so we know that their acceleration is not 0. Alright, so we're given force A and force B, not the x components, so that means we need to do a trig substitution. So since the 25 degrees is adjacent to FA of x, I'm going to do the hypotenuse times the cosine at 25 degrees. And then for force B, the 35 is adjacent to force BX, so I'm going to do hypotenuse times the cosine of 35 degrees. And that's going to equal mass times acceleration in the x. Now I'm given force A in the problem, so that's 200 newtons. And I'm given force B in the problem, that's 300 newtons. And I know that the mass of the box, or present, is 25 kilograms times acceleration in the x. So from the x direction equation, I can find the acceleration in the x direction to be 2.58 meters per second squared. So I've answered the first question to this problem. Now let's look at part B. Part B wants to know what the force normal is. The force normal is in the y direction, so let's do our y direction equation. So we have force normal in the positive y, the weight of the box in the negative y, and then we have a force A in the negative y from child A, and force B in the y from child B in the y direction. Okay, and then we're going to have mass times acceleration in the y direction. Alright, so force normal is our unknown. We can sub in mg for the force due to gravity. Force A is, in the y, is opposite to the 25 degrees, so we're going to use hypotenuse times the sine of 25 degrees. And then force B in the y is opposite to the 35 degrees, so we're going to use hypotenuse times the sine of 35 degrees. And that's going to equal mass times acceleration, and acceleration in this case is going to be 0 because we're pulling the object along the horizontal surface. We're not pulling it up, and so it's not lifting up off the ground. So because we're pulling it along the horizontal surface, it stays flat on the surface, so you're only moving the x, not moving in the y. So this means that the force normal and child B are balancing out child A and the weight of the box. And I'd like to do a problem like this to show you guys that the weight and the force normal are not always equal to each other. If you have other forces acting in the y direction, they have an effect on what that force normal needs to be, because with child A pulling down more, that increases force normal, but at the same time child B pulling up is decreasing the force normal, because the force normal responds to what else is going on in the y direction. So we can plug in the mass, and the mass was 25 kilograms times 9.8 meters per second squared minus 200 newtons times the sine of 25 degrees plus 300 newtons times the sine of 35 degrees is going to equal 0 newtons, which gives us then a force normal of 157 newtons.